Sanjeev. So I begin by thanking Prasanta and other organizers for organizing these very nice meetings every year, and especially because it's online and allows a lot of students to actually listen to talks. Physical talks, of course, have some advantage, but that is a limitation that not so many participants can attend. So I think this is one plus point. So I chose this I chose this topic because I think from what I have been seeing, this two particle interference is something on which not much has been talked about in these meetings. So that's why I chose this topic. So outline of the talk is the following. So first, I'll give a brief overview of this single particle interference and wave particle duality, and then I'll come to two particle interference, which has basically two experiments, two effects: Hong-Ou-Mandel effect, Hanbury-Brown-Twiss effect, and then I will show the equivalence of these two effects. Okay, so let us begin by looking at this simplest experiment, which has been considered to be the most beautiful experiment in physics. So there are particles which are coming from this source, and there is a double slit sitting here, and there is a screen sitting here. And particles are coming one by one, not all together. I have just drawn them together, but assume that one particle comes and hits the screen, then the other particle comes, and so on. So if you close one slit and keep only the upper slit open, what you see is that there is a pattern on the screen right in front of the slit. There will be maximum number of particles, and then particles will be lesser and lesser as you move away from the center location. Similarly, if you have the upper slit closed and only the lower slit open, the pattern will be almost exactly the same, only that center may be slightly shifted. If these two are very close, these two slits are very close, then these centers will be almost overlapping. You can't even differentiate. So these two will be the same. So since particles are coming one by one, and you would know, you would intuitively think that when a particle comes and passes through the slit, it will probabilistically somewhere fall on this pattern. And if it passes through the upper slit, it will fall somewhere on this pattern. So since it's a particle, the experiment can be done with electrons, neutrons, and so on. So each particle will pass through only one slit. So it will land on one of the two patterns. So when both the slits open, what we expect is that this will be just a sum of these two patterns. If a particle passes through the upper slit, it will fall on this some pattern, and if it goes to the lower slit, it will fall on the other pattern. So it should be just a sum of these two patterns. But when you actually do experiment with quantum particles, what you see is the following: that overall spread is the same, but there are regions in which there are no particles, there are regions in which there are no particles, and there are some regions on which particles are concentrated. So these are what you are familiar, fringes. So this is the bright fringe and separated by dark fringes. So this is very surprising that although particles are coming one by one, and each particle presumably is passing through only one slit, how does it make a difference whether the other slit is open or closed? But it seems to make a difference. So then people thought, let us try to find out which slit is the particle is passing through. So you put some kind of a path detector. This could be a very sort of non-disturbing measurement. What you might think that you have a camera, suppose these are neutrons, you have a camera, it will take a picture of these every particle which is passing through. So one can show that as soon as you have this kind of mechanism installed, which can actually find out whether the particle has gone through the upper slit or it has gone through the lower slit, immediately the interference is gone. And you get just the sum of these two initial results. So this is what you had expected when both slits are open, but when both slits are open, this is not what you get. But if you put a path detector, if you find which path the particle has followed, then that interference disappears and you get this sum of two patterns. So interference here, this is very familiar with very similar to the Young's double slit experiment, which is done with light, and that established the wave character of light. So here, the natural conclusion will be that these particles, they may be massive particles, they are actually behaving like wave. And when you find out which slit the particle is passing through, it is now acting like a particle, that it is passing only through one of the slits. So this experiment seems to show that this wave nature and particle nature, they are actually mutually exclusive. So Niels Bohr was so fascinated with this concept that he elevated it to a separate principle, which he called this principle of complementarity. So for the two-slit experiment, it will mean that the which path information or which way information and the existence of interference are mutually exclusive. And Feynman, in his lectures on physics volume 3, he has talked in detail about this experiment, that any way of finding out which way the particle has gone will destroy the interference. So he says that this is a phenomenon which is impossible, absolutely impossible to explain in any classical way, and which has in it the heart of quantum mechanics. In reality, it contains the only mystery. Okay, so as I have described to you, this seems to be two properties seem to be mutually exclusive. So now let me ask this question. Let us ask this question: that can it be made more quantitative if we try to observe wave nature and particle nature at the same time? Can we do it in a sort of fuzzy way at the same time? Maybe partial wave nature and partial particle nature. So this is what I call quantifying this wave particle duality. So this can actually be done. So now suppose we have this double slit experiment, and there is something which I call the path detector. So let us not bother about what this is. This could be a simple mechanism. This could be a very complicated mechanism. This path detector may be an external device. It may even be a property of the particle. For example, it could be a polarization of the particle, which with which you can find out which slit the particle has gone through. And so let us not bother about this. Only thing we will assume is that when the particle goes through the upper slit, this path detector state is D1. And when it goes through the lower slit, the path detector state is D2. So the problem of detecting the path now boils down to finding out, distinguishing between these two states, D1 and D2. So, and then you will see interference here. So there is a standard optical way of defining visibility of interference. So that we'll call visibility. And this, we have to now formulate some distinguishability of the two paths. So basically, which will be based on distinguishing between the two states. So there are two ways of distinguishing between these two quantum states. One is called this minimum error discrimination. So based on this, Engler defined distinguishability, and then he formulated this relation: d square plus v square is less than equal to 1. So extreme cases are that if you have full path information, so both these quantities go between 0 and 1. So if you have full path information, that means this is 1. So to satisfy this relation, v has to be 0. So which means we will not get any interference. And if you see interference with full visibility, that means v is 1, then distinguishability has to be 0. So which means you cannot distinguish between which slit the particle has gone through, or rather these two states will be indistinguishable. So this was done in 1996, and this has been a popular duality relation. So recently, but this was done for us, proven for a symmetric case. If you have asymmetric kind of situation, that particle is more likely to go through one of the slits. So this doesn't directly hold for that. So for this general case, we had worked on this, and then we use, instead of having this minimum error discrimination, we use what is called unambiguous state discrimination. In an unambiguous quantum state discrimination, it works the following way, that the measurement results on D1 and D2, they fall into two categories. In one category, you can distinguish without any error, whether it is D1 or D2. Or in the other case, you know that your distinguishing has failed. So if you fail, you will know. And if you do not fail, then also you will know, and you will know which one and which one of these two. So there is no error in this. So we establish this relation D plus B less than equal to 1. So this D and this D are actually different. So these relations were actually experimentally verified last year by Franco Nori, who was the inaugural speaker yesterday in this meeting. So he and his collaborators, they have actually investigated both these relations, and they have a surprising conclusion. They say that this linear duality relation, that means this one. So they conclude that this linear duality relation is tighter than the quadratic duality relation. This even we had not thought that for two slits it will be better. For more than two slit experiment, we know that this is actually the a good relationship, and this thing doesn't work for more than two slits. But even for two slits, these experiments have shown that this relation is tighter. Okay, now let us go to two slit experiment. So this first experiment, and which was a very sort of, in some sense, a shocking experiment, was done by Mendel's group, Hong-Ou-Mandel. So you have now, so in this double slit experiment, which I had shown before, you had one particle coming and passing through two slits. But here you have actually two sources. So you have source A and you have source B, and then they travel in a particular direction like this. And then there is a beam splitter. So this is a 50-50 beam splitter. So the particle which comes from here, this can either transmit or it can get reflected and reach this. If it transmits, it will reach D2. Same thing happens for this particle coming from source B. So it will either go here or go here. So since they are independent particles, you would think that there is equal probability of this particle going here and equal probability of this particle going here. They should not affect each other because they are independent particles. But this result was very interesting. If you tune the timing of this very precisely so that both these photons, so this experiment was done with photons. So if both the photons arrive at the beam splitter exactly at the same time, then you see this dip. So let me just explain that there is a coincidence counter sitting here, which will count particles when one reaches here and one reaches here. So if one particle is detected here, for example, if both particles are found here, then this will count 0. But if one particle is detected here, one particle is detected here, then this will count 1. So that is how coincidence counter works. So, and this on the x-axis is the position of the beam splitter, which actually establishes the time difference between the two photons. So at this point, the time is same. Time of arrival at this beam splitter is the same. So here, the coincidence count actually goes to 0. So which means that particles they either all go to D2, both particles go to D2, or both particles go to D1. Never will you see the case that one particle has gone to D1 and one particle has gone to D2. So that means the coincidence count will be 0. So you see that coincidence count is 0 at this dip. So this is the famous Hong-Ou-Mandel dip. So this was a very surprising experiment. And of course, a lot of work has been done on this. So what this Steinberg and collaborators, what they did was that they did this now with photons coming from the two sources, and photons may be partially polarized. I mean, they will be polarized in maybe different directions. So what they observed was the following, that when this polarization is in the same direction, then they see the dip which is the deepest. But if the polarization of the two photons, they have an overlap with each other, then you see that dip is still there, but dip is now shallow. So you get, if you define in some way the visibility of this, so you will see that the visibility of that dip has gone down. And when the polarizations of the two photons, they are completely orthogonal, then you see that dip completely disappears. This straight line here, this is that. So it seems to say that when photons are made more distinguishable, so because photons are identical particles in a quantum sense, if they are polarized in a different way, then actually you can distinguish them, otherwise you cannot distinguish them. So here it seems to suggest that if photons are made more distinguishable, it suppresses the home dip, or it suppresses the two particle interference. So now the question which we are asking is that, does a really complementarity principle exist for this two particle interference? Can it be quantized, quantified? Can it be quantified that if you define a distinguishability between the two particles, can there be a duality relation between this distinguishability and the visibility of this two particle interference? So this is the topic I will discuss now. So let us consider a general kind of home experiment. It may be done with photons, it may be done with neutrons, but all we assume is that they are identical particles with an internal degree of freedom. So for example, if they are photons, then they will be, it will be you can use the polarization as the internal degree of freedom. If they are neutrons, you can use the spin of the neutron. So for example, there are two neutron sources, and one is throwing out neutrons with the spin up, and the other is throwing out neutrons in the spin down. So you have completely distinguishable neutrons, and that should not show any two particle interference. So now let us consider the scenario in which these two states, dA and dB, they are the states of the internal degree of freedom. They may or may not be orthogonal. In general, I'll assume that they are non-orthogonal. So this two particle state, for these two particles, I will write it in this way. So normally you would write it just psi A1, psi B2. So psi A represents the spatial state of particle 1, and this represents the spatial state of particle 2. And then together we have this internal degree of freedom. Since they are identical particles, you have to have a symmetric wave function. So I'll write a symmetric term where these particle labels 1 and 2 have now been swapped. Otherwise, everything is the same. So then these symmetric state, it comes and impinges on the beam splitter. So let us, in the simplest way, find out what will be the effect of the beam splitter. So for example, if the particle is in the particle coming from source A, it falls on the beam splitter. So let me just show you this thing again. So it's from the source, it falls on this. So you know that it will either go here, it will go here. So before hitting, it will be in a superposition of D1 and D2. So these are the states which I am describing as D1 and D2. So it will be in a superposition of D1 and D2. And same way, if you have a particle coming from source B, you will have this superposition D1 and D2. And you might ask why there is a minus sign here and there's a plus sign here. There is a difference. People from optics would know that reflection from the upper surface and the lower surface in a half-circular mirror actually makes a difference in the phase of this. So that is the reason for this phase. So now the two particle state after the beam splitter, after they have passed through the beam splitter, is the following. So just you apply this U operator on this state. So this is what you get. D1 minus D2 for particle 1 into D1 plus D2 of particle 2 plus D1 minus D2 of particle 2 and D1 plus D2 of particle 1. So now probability of a coincidence count. How would you calculate the probability of a coincident count? Just take an inner product of D1 and D2 because you want coincident count means that one particle has to be found at D1 and one particle has to be found in D2. So you have to take an inner product of this D1 and D2 with the state of the particle which has passed through the beam splitter, which is this U acting on psi. But there is another term, because you might have particle 1 coming to beam splitter, detector 2, or you might have particle 2 coming to detector 2. So you should have two possibilities. So they are basically sum of two probabilities. And this gives you the following. So you see that what you get, this probability of coincidence count is actually finally half into 1 minus inner product of dA dB mod square. So when the two particles do not arrive at the beam splitter together, anyway, there is no interference, and then just coincident count maximum is half. This we already know. When the particles arrive at the beam splitter together, then this coincident count is minimum. I mean, however minimum it can be, it is actually this. This represents interference. So we can define a visibility of this Hong-Ou-Mandel dip, Cmax minus Cmin divided by Cmax. And you see that this is just equal to inner product of dA and dB mod square. So which you can see right from here that if dA and dB are completely orthogonal, this will be 0, so that visibility will be 0. For completely distinguishable photons, you will not see any Hong-Ou-Mandel dip. So now to find out whether this particle came from source A and source B, this we cannot know. Only thing is that we can distinguish it between the two particles. Additional degree of freedom can distinguish between the two particles, whether it is the state dA or state dB. So now if we use this unambiguous quantum state distribution, which discrimination, which I had talked about while talking about single particle interference, then if you are given, if a particle comes, you don't know whether it is coming from source A or source B. For a detector, you have just a photon coming. Since photons are identical, you have no way of knowing whether it came from source A or source B. All you can do is you can distinguish what is the polarization, whether the polarization is dA or the polarization is dB. And if they are not orthogonal, so the maximum probability of finding out without any error, the probability of distinguishing them is just given by 1 minus dA inner product dB. So this I am not deriving. This you can actually read up. This is a standard result from this UQST, unambiguous quantum state discrimination. So maximum probability is this. So now based on this, we define a particle distinguishability as D equal to P max into 2 minus P max. So you will see that this relation, this quantity D also goes from 0 to 1. If P max is 0, then this will be 0. If P max is 1, then this is 0. And this will again be 1. So we can define a distinguishability as 1 minus inner product of dA dB. So if you calculate this from here, what you'll get is this. So this is our distinguishability. Now together with this visibility which we found here, it gives you a very nice and cool linear complementarity relation. D plus V is precisely equal to 1. So this is a duality relation for two particle interference. Duality between what, or complementarity between what? Complementarity between distinguishability of two particles. How well can the two particles be distinguished, and the visibility of two particle interference. So incidentally, just this year, this new duality relation for two particles has been experimentally tested by this group in China. This paper is still in accepted manuscript in this journal. So they don't use a polarization, they just do a time kind of marking, which I don't have time to go through right now, that they do a temporal marking of these two photons which are coming from two different sources. And they have defined a distinguishability exactly in the same way which we have defined. And then what they do is, for various distinguishability of these two photons, they actually plot. This is distinguishability and this is visibility. So distinguishability is in blue and this visibility is in red. So you can see that here the visibility is close to 0 and this distinguishability is close to 1. And then as distinguishability goes down, visibility goes up, and then they just go on. So there is you can see a complementarity here. And this relation, they are able to actually saturate this relation. In non-ideal cases, actually it should be an inequality less than or equal to 1. This is only the ideal case. So experimentally, they have actually been able to go to the almost ideal case. Here they have plotted V plus D. So in the ideal case, V plus D should be equal to 1. And you can see that these are their experimental points and this is the theoretical line. So they are very close to 1. So that means this two particle duality relation has also been experimentally established for this Hong-Ou-Mandel experiment. So now let us come to another experiment, which is actually older than this. So this Hong-Ou-Mandel experiment came in mid-80s, and Hanbury-Brown-Twiss experiment was proposed in 50s. It was first done classically and then much later quantum mechanically. So classically, classically, the way it was done was that the idea of this experiment was to have sharper measurements of astronomical objects, because if you want to distinguish, if you want to differentiate between two stars which are far away, so it was based on that. So you have two sources coming here, and then light from these two. So let me just assume that they are now classical waves. So classical waves coming from here. So waves, they will spread out, and there will be a wave coming from here, which will be spread out over this region. And you have another stationary source, which is at a distance from this source A. Here also, another classical wave is coming, and then it is again spread out over this region. And here you have two counters sitting here, two detectors sitting here, not counters, two detectors sitting here, and there is a coincidence counter. The difference is that now these two detectors are movable. They can change their positions. So obviously, if there are two sources, and unless they are very precisely coherent, classical sources are not coherent. So if you fix one and you only move the other one, you are not going to see any interference. So no interference was seen. So classically, you know that, say, for example, from this source, the wave from this source at point RA and RB, sorry, at one point, say X1, there is waves coming from here and waves coming from here. So the field can be written at EX1, this point X1, as alpha times e raised to the power I k RA1, RB2. This RA1 and RB2, you can see that this is what these distances are. So again, you can see that there are likelihood of this wave coming here, this wave coming here, and same way this wave from source B can also reach both the detectors. So if I calculate the intensity at this detector X1 coming from both the sources, I will get this expression. There is a cosine term here, sitting here. So you might think there is an interference, but then there is a phi sitting here, which is phi is the phase difference between these photons coming from here and here. So you know that these sources are incoherent. So you have no control over the relative phase between these two waves. So finally, you have to average over this phi. When you average over this phi, this term disappears. So interference is completely washed away because of these random phases. Now, instead of looking at interference at one detector, what you do is you detect wave here and detect wave here, and you correlate their intensities. So this is the intensity correlation. So IX1 and IX2. So this is the way I had calculated IX1. So similarly, you can assume that IX2 can be calculated, and then I multiply them. So you get this. So there will be this expression, and this has to be averaged over all phases. So you can convince yourself that when you do this, this phi term will completely disappear, and you will get this expression. There is a cosine term which remains. And cosine term has what? This can be manipulated. This, it will be actually difference between X1 and X2. It can boil down to a difference between, because these two are fixed, these are moving. So this cosine term will be a function of X1 minus X2. So that means as a function of separation between these two detectors, you will see an interference. So this was a very surprising feature. And this, since it does not depend on the phases of these two, these phases could be widely fluctuating of these two sources, still you will get this interference. So you can you chemical observations, because photons coming from two parts of an astronomical objects or different astronomical objects, they can still show interference. So there will be more accuracy in their measurement. But you see that if you define a visibility of this interference, visibility is given by this expression, and this is bounded by half. And you might be able to guess why it is half, because there is equal probability of this going here and going here, equal probability of going here and here. So there are in 1/4 situation you will have this particle going here, and another 1/4 this particle going here, and this particle going here. In the other 1/4, both particles will land here, and this other 1/4, both particle will land here. So that means 2 1/4 1/4 will give you the coincidence count. That will be just half. So then they proposed that this experiment should be done with light. So this was done with classical waves. So this should done with quantum light. So initially there was a lot of opposition. People thought that this experiment simply cannot be done with quantum light or with photons. Why? Because you see that here it seems to be interference between wave from here and wave from here. And the standard quantum mechanics says that a particle interferes with itself, not with another particle. So in this Dirac's book of quantum mechanics, he has written it very clearly that each photon interferes with itself, not with another photon. So people thought that this will imply interference between two independent photons, and that cannot happen. But this experiment was done, and with photons, single photons, and they actually found this Hanbury-Brown-Twiss effect for these two photons also. This experiment was done with various things like atoms, which are bosons, atoms which are in this thing, Bose-Einstein condensate, they are acting like bosons. So they also show this Hanbury-Brown-Twiss effect. So now let us ask that if these, so here again photons have to be identical, and that is what leads to this Hanbury-Brown-Twiss effect in this quantum situation. Now we are asking this, that if we make these two photons or these two particles in general partially distinguishable by some internal degree of freedom, how does it affect this interference visibility? So again, you see that I have now defined these Gaussian wave packets, one Gaussian wave packet emerging from one source, this other Gaussian wave packet emerging from the other source, and this one has this internal degree dA, one other has internal degree d2. Since they are bosons, you have to have a symmetric term again here. On arriving at the two detectors, the probability of finding a photon at a particle at x1 and another particle at x2 at a later time. So you see that these were Gaussians, and this, with time evolution, there will be this term delta. So you need not go into the detail, but you just know that this time is actually sitting here in this delta. So time is hidden here. So time evolution is here. So you will again have this Gaussian, but now with this complex bits. So now very easy to see coincident count. You just take a mod square of this. It will give you the joint probability of detection at point x1 and point x2. And the joint probability will give you this. You see 1 plus dAdB. Oh, actually, I forgot to mention that I had written eta instead of 1 here, because if eta is 1, then this will be a case for bosons. If these are fermions, then this eta will be -1. So you can do this with electrons, which people have done. And you have what is called the anti-Hanbury-Brown-Twiss effect. So you get this Hanbury-Brown-Twiss interference term, 1 plus cos of this. You can see that when cos is 1, this will be maximum 1 plus 1, 2. When cos is minus 1, this will give you 1 minus 1, 0, 0 intensity. But you see that this is inner product of D and dB is sitting here. So you can very well guess that visibility of interference will be governed by this term. And indeed, if you calculate using the standard way to calculate interference visibility, that visibility here also is given by the mod square of inner product of D and dB, which is bounded from above by 1. So particle distinguishability, again, we'll follow exactly the way we had defined particle distinguishability for the Hong-Ou-Mandel experiment. Using that distinguishability, again, we find exactly the same relation, D plus V is equal to 1. So you can see that there is a complementarity between HBT, Hanbury-Brown-Twiss, HBT interference visibility, and particle distinguishability. And same duality relation holds for both Hom and HBT experiment. So this indicates that they should have a common origin, but historically and even today, a lot of people believe that they are completely different experiments. Hom was conventionally done using classical waves. HBT Hanbury-Brown-Twiss experiment was done first with classical waves and later shown to be true for later shown be also valid for quantum particles. And this Hong-Ou-Mandel experiment was done straight away with single photons with quantum light. And people believe that Hong-Ou-Mandel is a purely quantum effect. This cannot be shown classically with classical light. But our analysis seems to show that there is a common ground between these two, and we'll come back to it later. But first, let me show you something more. So you must have heard for single particle interference that there is a concept of quantum erasure. That if for a single particle interference, if two paths are completely distinguishable, then this interference is completely lost. But when the particles have already gone through the double slit, if you somehow erase this path information, then this interference can come back. So this is called this quantum erasure. That this path information, which is sitting in some kind of a quantum path detector, which has not been measured yet, which is still in unmeasured quantum state. If you erase that information in some way, then interference can come back. So this has been shown. So in this experiment, Steinberg's group, they showed that indeed for two particle interference, two photon interference on this Hong-Ou-Mandel experiment, this quantum eraser works. They did the same thing. They have photons from two sources with different polarizations coming, and you see that interference is completely lost or passing through these photons before detecting through a filter, which makes that their polarization, which projects their polarization onto the same state. This Hong-Ou-Mandel dip, which had disappeared, can actually come back. So this quantum erasure has been demonstrated for this Hong-Ou-Mandel experiment. But people, interestingly, have never thought that this quantum eraser can work in this Hanbury-Brown-Twiss experiment also. So since we are analyzing these two experiments in the same footing, I will show you from a very simple analysis that quantum eraser can work in this Hanbury-Brown-Twiss experiment also. Okay, I think I'm running short of time, so I'll just go fast. So you will see that I've written this state which I have shown before, two particle state in the Hanbury-Brown-Twiss experiment, two Gaussian wave packets, and with the internal degree of freedom. And the interference is here. And you know that if two states are orthogonal, suppose D and dB are orthogonal, this term will go away and you will not see any interference. So now you assume that you have this situation that D and dB are completely orthogonal, but what you do is first put filters before these two detectors, and filters are such that it will allow only photons with dA plus dB by √2. So both the detectors have these filters. They will allow only photons which have a polarization dA plus dB divided by √2. If you do that, do it on this state, the state becomes this, and you can guess very easily from this state that this will show interference. And I'm not going into the detail. So you will see that for this completely distinguishable photons, if you put this filter, this interference comes back, you can see this blue line. On the other hand, if you put a different kind of filter which allows only states with dA minus dB, then you will get an interference which will be slightly shifted, the one which you can see in this dotted red lines. So you can see that now we have demonstrated quantum eraser for both the Hanbury-Brown-Twiss effect and for Hong-Ou-Mandel effect. We have seen that the same duality relation holds for both. So there has to be a common ground. So let me now explain how these two are similar. In fact, they are the same. So first look at this single particle interference. You have this is a simple double slit experiment, which I had shown you before. You have a single light source, and source is such that light spreads out. It falls on both the slits, and then it passes through the two slits. But when it passes through the two slits, again, when it comes out, it spreads into a broad region. So from here also, it splits into a broad region. So this is a broad region from which particle coming from here and particle coming from here, they overlap, and then you see an interference pattern. So this you all know very well. But you also must have heard about this Mach-Zehnder interferometer. Mach-Zehnder interferometer, what you do is you have photons coming in a straight line. They don't spread out. They come in a straight line, and then there is a beam splitter which splits into two paths, two discrete paths, not a continuous set of paths. So this will get combined at this. There is another beam splitter which combines these two paths. And you can see that passing through the double slit, that role is played here by the beam splitter. It splits into two parts, and when this light spreads out from these two slits and overlaps, that role is played by this beam splitter here. It will split this into two parts here. It will split this onto two parts here. So these two parts now will be mixing. This part will be mixed with this one here and also here. So these two experiments are completely equivalent, only done in a different way. And indeed, this single particle wave particle duality relation holds for both these experiments. Now, look at this Hanbury-Brown-Twiss experiment. You have, so it is exactly like this experiment, except instead of one source and this particle going through two slits, you have one particle going through here, one particle going through here. So in some sense, there is one source sitting here, one source sitting here. So that is the only difference. Otherwise, everything is the same. So after coming from this slit, it spreads out over a region. This also splits out over a region. Here also, coming from source, it splits out over a region. It splits out over a region, and you see interference. So this is the Hanbury-Brown-Twiss effect. What is the Hong-Ou-Mandel experiment? You have again two sources, and as here, in contrast to this, there were discrete paths. So here again, you have two discrete paths, but again coming from two sources, just like here. So instead of continuous spread here, so these are particles going through well-defined paths, and the mixing of these two paths is done by a beam splitter. And when they come out, again, the mixed paths are again discrete and two in number, exactly like this. These two detectors here, they get contribution from this path and this path, and so same way this detector gets from two discrete paths. So you see that these two experiments, the relation between these two Hanbury-Brown-Twiss experiment and Hong-Ou-Mandel experiment, this is a relation between these two is exactly the same as in the two-slit interference and the Mach-Zehnder interferometer. And as same duality relation holds for both, it is not surprising that what we have shown, that this two particle interference duality relation, same relation holds for both these experiments. So both are actually the same effect, only experiment. And these two effects, Hong-Ou-Mandel and Hanbury-Brown-Twiss effects, are completely equivalent in essence. Thank you.
Yeah, thank you, Tabish, for a very nice talk. We still have like about 5 minutes for questions. So anybody has any question?
Yeah, Chiranjeev, maybe I can ask a question.
Yeah.
See, Tabish, you mentioned about the similarity between two-slit experiment and SBT.
Right.
But in two-slit, the source is one, right?
Yeah, here the source is one.
So there will be phase, therefore, these two people who are going away, we can actually see there will be a constant relative phase difference between them. Right?
Just come again.
Essentially in the SBT, you have two different sources. So there is no correlation between them to start with.
Right.
Whereas here, light source is one in case of two-slit. So therefore, that there will be a phase correlation between the light who are coming out.
Right. So, and yeah, that is true. That phase relation also has to be maintained in order to see the interference.
Yeah.
If phase fluctuates, so I agree with you. And these two experiments, they are actually immune to the phases of the two sources.
Yeah. Thank you.
Okay. Any other question?
So, hello.
Yeah.
So, can I say that the interference pattern is arising due to the phase induced by the spatial distribution of the detectors like X1 and X2? Means interference comes from kind of like not from the phase not coming from the source, but phase coming from the location of the detectors like X1 and X2 here over here.
See, if for this Hanbury-Brown-Twiss experiment, if these two are exactly at the same location, you can have these two very close also.
Okay.
So anyway, so interference will make sense. You are seeing this interference variation in the intensity of coincident count as a function of distance. So if you see just at one distance, you will see some intensity, and you will not be able to make out what is the interference. So just like saying that if you just look at one point here, either you will see a dark fringe or a bright fringe. That will not give you an idea of what interference is. You have to sort of move over some distance. So here, the same thing can happen. The same thing will happen. But spatial separation is not crucial. If they are very close together, then also you will see there is an effect of these two photons interfering with each other. In fact, this can be interpreted as this photon bunching. This is not a very nice way. A lot of people actually think that in this they are always either together or separate. So this is like bunching, but this Hanbury-Brown-Twiss experiment, yeah, good actually this point came up. This actually cannot be explained so easily by bunching because there are some discrete distances between these two for which this coincident count goes to 0. So that means particles land up at both particles land up at say one detector and not one here and one here for some discrete distances.
Okay.
So I don't think this can always be talked in terms of bunching. And for some other separations, both particles will either one will go here, one will go here. They will never come to both at one point. So bunching argument goes through here, but bunching argument doesn't always go through Hanbury-Brown-Twiss experiment.
Okay, thanks. So
Okay,
we
I see.
have
Thank you, sir.
one quick question maybe.
Sir, I have a question.
Yeah.
The last
Sir,
question. The last
sir,
question. Okay.
Sir, in HBT, we are saying the interference in varying the detectors spatially, like
Right.
when we move them, then we are seeing the interference.
Right.
But in Hong-Ou-Mandel experiment, we are seeing with the time, right? Like when both are coming at same time, or like
no, both are coming for the time. That is the tuning that has to be done in order to see interference. So that means coincident count between these two detectors will go to 0 only when they are tuned such that both arrive here at the same time. This happens here also in this Mach-Zehnder interferometer. These two phases of the two paths, they have to be matched exactly. Then only all photons will go only to one detector and none will go to the other detector. So this dark fringe will be observed only when these phases have to be matched precisely. So there is a good equivalence between these two.
okay.
Yeah.
You
Thank
mean
you.
when both?
Yeah.
Sorry, one.
Yeah, thank
So
you.
when both
Very
the
nice. Yeah, thank you.
Is that fine, Lava Kumar? Okay. Okay, thank you, Tabish. Thank you very much for wonderful talk. And we learned a lot today. So we'll go to the next talk of the session, last talk. And that is Arman.